Don't the directions say the table of contents is required? Is that right?
Yes, sir.
Yeah. Okay, guys, let's get started. Previous page there. Why would we want to put a halogen alpha-2 carbonyl like this? Well, for one reason, very common reason, is the halogen is now a leaving group, and we can do leaving group chemistry, SN1, SN2, E1, E2. Treat this with a sterically hindered strong base. What are we going to get? Anybody? What about that alkene? By what mechanism?
E2 elimination?
E2 elimination. You know that mechanism, right? Yeah. And what type of product did we make? Yeah. Alpha beta unsaturated carbonyl. Carbonyl, but the alpha position and the beta position, you have unsaturation now. And this is a common way to make alpha beta unsaturated carbonyls from saturated. One from here to here requires removing two H's. That would be an oxidation. That's kind of difficult here. But this way, add a leaving group by alpha halogenation, and then do E2. And now what are we essentially removing? We're eliminating HCl by our E2 elimination mechanism. Okay? Alpha beta unsaturated carbonyls. We will see another way to make such compounds in a little bit. Number 6. Not quite sure what number 1 through 5 were, but I'm sure it's on the previous pages. And I'm not sure what heading we're under, but this is number 6. What is the heading we're under?
Alpha halogenation.
This is number 6 under alpha halogenation?
Yep.
Okay, well, it's not halogenation, but it's sort of a variation of that. Exhaustive deuteration. Not exhaustive halogenation, but deuteration. Take this compound here, aldehyde or ketone. We can exhaustively deuterate each acidic hydrogen. 2 here, 1 here. The acidic alpha CHs. Again, relatively acidic compared to the other ones. Somebody may look at this and say, there's no acidic H's here. Yeah. It all depends on how much, what is really an acid. Are you really calling these acids or not? Okay, you know what I'm talking about, right? It's all relative. Alpha CHs are acidic enough to do chemistry. The other ones are not. We're never going to do any chemistry down here, but these 3, 2 and 1, we can do chemistry here. Basic conditions, we can generate enolate, for example, here. With D2O, we can just put proton back on, but instead of H, this can put a D back on, and D2O serving as the deuterium source. And you just do that 3 times, and now you've replaced the 3 H's with 3 deuteriums. Exhaustive deuteration. What's it good for?
Can you show where your acidic H's are?
Absolutely nothing.
Yikes.
What's it good for? Well, mass spec. This is often used in mass spec as a little trick. This has a massive M. This has a massive M plus 3 because deuterium is a mass of 2 versus hydrogen 1. So each deuterium you add, you're increasing the mass by 1. Mass by 3. Increased mass by 3. And sometimes Well, you can use this as a trick. Run mass spec of this and you get mass of M. Still don't know what your compound is though. The mass is 360, but I don't know what the structure is. I could run all types of things. One other trick I can do is I can treat this compound, which I don't know what the structure is, with excess D2O and KOD. By the way, the KOD, which is the hydroxide which took the H, that's actually catalytic, right? It's actually catalytic because when this takes the D, what are we reproducing? What are we reproducing right there? OD minus, like OH minus. So it's actually catalytic. We do this and the mass increased to, it went to 363. What does that tell us about our molecule?
It has 3 H's that could have been replaced by a deuterium,
3.
like acidication.
There you go. It has 3 H's that are acidic enough to do this chemistry and get replaced by deuterium. Not 6, not 9, but 3. And because mass spec tells you this number and then this number, and so knowing it has 3 acidic H's, that's useful information. Well, if you, then this may be done in bulk. You can then turn around and remove the D's by treating it with H2O and KOH, or sodium hydroxide, because hydroxide will take the D. That's just a special H with an extra neutron, right? I mean, it's the same thing. Hydroxide takes the fancy H, make the anion, and then the anion takes an H from water. But see, here you flood it with H's, and over here you flood it with deuteriums. And you can take these back off and replace them all with regular H's. If you were doing a bulk sample, okay? This compound here increases in mass by how much we're treating with D2O and sodium deuteroxide?
+8.
Basically, the question, how many acidic H's?
8.
8.
2 here, 1 here, right? 3, 5, 3 more there. Yeah, it would increase by 8. These are probably not acidic enough. We can do resonance of the anion, but a benzylic CH is usually not acidic enough to do chemistry with hydroxide. Got to be careful here, because what if this compound had like an OH here? Well, as we learned with NMR, you treat this with D2O, you're going to convert this to OD. Well, OHs are even more acidic than CHs. I mean, that would get replaced too. So it's not just CHs. There could be other H's in the molecule that get replaced. But in these examples, it's just the acidic CHs. So what's it good for?
Mass spec.
A little tricky mass spec. Okay, B. A must have been alpha halogenation. B. Alpha alkylation. And we will expand this to acid derivatives such as esters and nitrides. Alkylation. First is direct alkylation. Next would probably be indirect alkylation. If we take such here, we know we can generate the enolate. But this equilibrium is not good. This is favored if we use hydroxide, because this plus water, right? How do you judge equilibrium? We learned in organic 1, pK of this. What's pK of these H's?
Oh wait. Yeah, about 20.
About 20. pK of the acid over here. Water, 16. Which side's favored?
The left.
Left.
Weaker acid. How much is that favored by?
10 to the 4th.
Fourth power.
10 to the 4. Okay? This is favorite. So at equilibrium, you've got way more of these. Okay? So this is not complete formation of the anion here when you use hydroxide as base. When you alkylate, you need complete formation of the enolate anion. How do we do this? How do we accomplish this? We need a stronger base. When you halogenate, hydroxide works. And there's some details there that we're not going to get into why and how it works. When you alkylate, you need complete formation of the anion. We need a stronger base. Most common stronger base to use here is LDA. I don't think we've seen LDA before. LDA. LDA is a nitrogen anion. It's also organic. Nitrogen anion, which is a stronger base than an oxygen anion. Oxygen's a better parent. Holds the electrons. It's not as basic. It's not as like, I'm mad. Nitrogen anion is more mad. I don't want to be minus. I gotta get an H. Where's there an H? Question.
How is it derived?
I thought you were going to ask me what was the name of it. We'll get to that. What's the name? What does LDA stand for?
Lithium diisopropyl.
Hmm?
Lithium diisopropyl.
Okay. Have you seen LDA before? Have you used LDA before?
I mean, it looks familiar from probably like a textbook.
Okay. What's the positive here? Yes, lithium. Lithium diisopropyl amide, or amine. Lithium diisopropylamine. What do we call anions of amine?
Yeah.
Right, this is unfortunate. What do we call an anion of chlorine?
Chloride.
Chloride. What do we call an anion of an amine? It's amide. But we know that an amide is also what? A functional group that has a carbonyl. See, it's called a misnomer. Okay. Usually when you hear amide or amide, you think about the functional group. But the anions of nitrogens are also called amides, because it's analogous to chloride. Okay. Lithium diisopropyl amide, or amide. Okay. LDA. Lithium is just most common. Mostly because of how it's made. It's made by treating the amine with like N-butyl lithium. N-butyl lithium is just the anion, carbanion. This has a pKa of greater than 40. This has a pKa of about 30. This takes the H, and we generate this plus what? Butane. These electrons take the H, leave behind, acid-base reaction. This 40 actually refers to what? It's a pKa, but that's acting as a base. What does this refer to?
Conjugate base.
Refers to the conjugate acid. That's what's 40. Okay, this is 30, that's size 40. Which side's favored?
The weaker side. 40.
The left side, the weaker acid side. This side's favored. Correct? N-butyl lithium will deprotonate this, and you'll form LDA. The lithium is there because this guy is usually lithium. Question?
Could you not just use N-butyl lithium instead of LDA?
Great question. Great question. We will answer that in a minute. And it's on the handout, so I'll wait till we get there. Yes, theoretically, LDA is strong enough to also deprotonate the carbonyl. And lithium is strong enough. So this is 16. Here, LDA is about 30. So that means this is 16. We make this plus the amine because now it took the H, 16, this is 30. Which side is favored here?
Right.
The right. So you see here, this is highly favored by how much?
10 to 14.
10 to 14, that's super highly favored. So while hydroxide is not favored, use of LDA, complete. Stronger base. We'll also mention, what's the purpose of the isopropyl groups? What do you suggest?
Sterically hindered.
Sterically hindered. Why? We'll point that out in a minute. Another reason is it makes it organic. It makes it more soluble in organic solvents. A base that you have seen before with H's here, and instead of lithium, sodium, which is NaNH2. We've actually seen that before. What was that used before?
Alkynes.
It's a traditional base used for deprotonating alkynes. Textbooks have always used it. It is a terrible base in practice. I don't know why. Okay? Textbooks need to be updated. Okay, this is 150-year-old information here. I don't know why they continue to use this. It's just because. But it's always used for deprotonating alkynes in textbooks, but never in the lab anymore. Okay? All right? We no longer use crank phones to call people. All right? Terrible base for one reason. It will not dissolve in any organic solvent because it's not organic. It'll dissolve in water, but you put this in water, it's just going to take an H from water, and all you got is hydroxide. The strongest base you can have in water is hydroxide. It's terrible. But that's called sodamide because it's sodium amide. But this is often called sodamide. Okay? The isopropyl groups make it much more soluble, and it will dissolve in something like THF, the diethyl ether. Even though it's a salt, anion, it will dissolve in organics because of the isopropyl groups. Lithium there also helps it dissolve, because lithium, things like this tend to be a little bit more soluble for some certain reasons than sodium. Okay? So there's some practical reasons here. So in the end, complete formation of your enolate anion using LDA. So we can now do chemistry. We take acetone, treated with LDA, one equivalent I assume here. What's that going to do? It'll generate the anion. Which side? Well, it's symmetrical. Now we throw in something like this. What chemistry can we have? Well, we see the product, so what's going on? Bam. Nucleophile, carbanion nucleophile attacking another carbon. Which bond did we just make? Right there, yeah? Carbon-carbon bond formation by an SN2. We could have showed this reaction in organic 1. We generate the carbanion by complete deprotonation of the carbonyl. Pretty straightforward? Good old SN2. How about the one below?
produce
anion
an even
here,
more.
yeah. And then this can alkylate. Uh-huh.
Dr. Stevens, the one below would produce an even more acidic H. Wouldn't it attack again?
Let's look at that. This would be that there, yeah?
Or would that be too sterically hindered?
Make that bond there, is that right? Did I get that right?
Yes.
Which one you talking about, Nick?
Wouldn't that also still have acidic H left that could still react again? Or would that be sterically hindered, as Lawrence mentioned?
Compound A?
No.
Yeah,
Second
compound
one.
B. The second one.
Well, what's the difference between compound A and the second one,
Oh, nothing.
in terms of your question?
Oh, okay. Not much.
Okay, so either compound, can it alkylate again? Yeah, you can alkylate again. But remember, this was one equivalent.
Oh, okay.
It's one equivalent unless we say otherwise, typically unless it says two equivalents. I mean, first step is this, done, there's no more LDA. You add just enough LDA to form this, it's complete, LDA is gone,
Okay.
and then this alkylates. You do not have any base to then come around, but yes, you can come over here again and repeat the process. The problem over here is it's no longer symmetrical, so where are you going to make anion at? You could maybe make an argument of one over the other, but it's no longer symmetrical. Starting was symmetrical. Here, we only had one place to make anion. You can also do this chemistry with other carbonyl compounds, such as esters. And we have the acidic. Now, what's the pKa of an ester here? Alpha C8. From the first page, it's practically 25, right? We talked about that. LDA is 30. It's actually more like 32 or so, I think. Maybe even 35, but even if it's 30, which side's favored, 25 or 30? 30. With LDA, it's still favored enough to get you complete formation of anion here. And then that anion will eventually find that electrophilic site that's partial positive due to the dipole of chlorine. And the magic of the chemistry will take place. We call that reaction SN2 if you're not familiar with it. And we get is that right? Benzyl chloride again, very reactive electrophile. What have we done to our ester? The original ester, we alkylated it, right? We added an alkyl group. Yes, that's what we're doing. At what position? Alpha alkylation. You can also do this with nitriles, cyano groups, because adjacent to the cyano group, it is acidic as well. We can deprotonate here. The pK is about 25. We talked about it on the first page. Resonance into the nitrile. And then we can come in here and, yeah. Boom, boom, boom. Cyano group, and then what do we have here? The ethyl. Alpha to the nitrile. Why not use n-butyllithium and generate the enolate?
Connect to the
Because you're like, okay, n-butyllithium, I want you to take the H and not add to the carbonyl. Can nucleophiles add to carbonyls? Could you envision that?
Yes.
In fact, we've done that before. That's like a Grignard adding to a carbonyl. Okay? Now, I've said before that acid-base reactions tend to be faster than other reactions. Yes, that's a general comment. But it is still possible that instead of it taking the H, you could add to the carbonyl as a nucleophile. And you would get that over there. And once you get that, it's game over because there's no leaving group. All you can do over there is just work it up and put a proton on. Okay? LDA is less likely to do this. Why?
Nitrogen is a weaker nucleophile? Because nitrogen is a weaker nucleophile?
It is slightly weaker, but it's still very strong. It's just, that's kind of like saying a small cannon is weaker than a big cannon. It's still a cannon. LDA is still quite nucleophilic. But the reason, we've already mentioned it, the isopropyl groups give it some steric hindrance. And steric hindrance hurt nucleophilic stuff, but sterics typically don't hurt acid base because the proton is so small. So, LDA typically will not add to the carbonyl, or it's designed not to. You might end up with that happening. The other thing is, if LDA did add, it's a nitrogen, and it could be, that could reverse. Because if this was a nitrogen here, which can we say that we could just come back in and kick that back off? Okay? So that's another thing that's good with LDA, where the butyl group is not going to get kicked back off. We looked at that with the beginning of the last handout, reversible, non-reversible reactions. So LDA is a common base there. There was a white handout along the way. Nomenclature, how are we doing with nomenclature? Also in the white handout was the Vidig. How are we doing? Put Vidig by video. Doing the Vidig reaction in lab. Any questions about that?
How did you want us to pick the R groups for the lab on Friday?
Would you like to choose an art group? You have a group and would you like to choose one? If you'd like to choose one, you can do that right now. Have you considered it?
Yeah, I mean, I know which group I'm working in, yeah. But I didn't know if you were going to assign us an R group or if we could just like...
I haven't thought about it too much. If you would like to tell me which one you want, we can reserve it for you. Do you know?
No, we haven't talked about it yet.
Okay, if you want to, maybe at the end of class, quickly let me know.
Okay.
And if you want to do that, first come, first served basis, and I'll just make a list, and if you say I want the bromine, I'll say, sorry, somebody's already chosen. So, yeah, you can let me know. I don't have any other method other than...
Okay.
If you don't choose it ahead of time, you'll just get one when you get in lab. But at that point, you will not have been able to do any search ahead of time.
Mm-hmm.
Vidig. While I have the white sheet here, the white set, there's a number of things here. One I can show because it's, well, you'll see. This one here, you got the white handout, lots of the application pages. I actually showed this handout before. This is in one of the previous packets, like from test 2 probably. Friedel crafts, yeah. Sulfur oxidation, which we're not going to do in this class, but that's a common reaction. But what's going on here? This is synthesis of Vioxx, so it used to be a $1 billion drug until it had heart toxicity. Side effects, what are they doing here though? Alpha bromination. Why? What do they then come back and do?
SN2.
They then come back with this carboxylate anion, and they displace it and make that bond there. Nucleophile displace the bromine. Then they do an aldol condensation, and we'll be looking at that in the next day or two. And this purple handout. Okay? And the one they're doing is an intramolecular aldol to make a ring. All right? All right. You guys never answered me, I don't think, about the lab report. You going to turn it in class in lab this week, or you want to do it Monday?
Monday.
If you want to turn it in this week, I'll accept it. Otherwise, I'll Monday here. I'll have to bring like 2 boxes or something, and we'll put each. Okay, Monday. Indirect alkylation. Also very common. And we'll have to talk about why you would want to do indirect. Look at this compound. 2 carbonyls. I'm going to first treat this with base. Which H's here are most acidic? You got alpha H's here. And here it's alpha to 2 carbonyls. What's most acidic? There's the best place to make anion. It's going to be stabilized not by resonance into 1 carbonyl, but resonance into 2 carbonyls. You can show 2 different resonance structures of that, 2 additional resonance structures. Of course, with anything, you can draw them and then say, hey, Dr. Stevens, does this look right? And I'll say, yeah, it looks right, good job. Or I can say, no, you missed something here. And that would be a valuable learning experience. I'm not going to draw them right here. Okay. But this is an example of a compound that has 2 electron withdrawing groups. And the CH is here. Instead of 20, even more acidic. With this particular one, pKa is about 12 instead of 20. Because of that, we can completely deprotonate with an oxygen base. We don't have to use LDA. And if you can do it with a more common oxygen base, which is more commonly found in the lab, cheaper, perhaps safer, because LDA could be a little bit more prone to causing a fire if you get it around water, it's more exothermic. You'd rather be able to use oxygen base. But note that I'm using sodium ethoxide and not sodium hydroxide. Why would we use ethoxide as a base? Okay, now let me go back over here and I'll deprotonate. Instead of hydroxide, the alkoxide, which can be used as a base. You know, in the past we generated such to do a Williams and ether synthesis. But we can also use this as a base. This takes the H, yeah. And I should have did it this way to begin with. This is going to generate the enolate here, alpha carbanion. Why use this base? Why not use hydroxide?
And it doesn't attack the carbonyl.
Tell me anything?
To keep it from attacking the carbonyl, it's stereochemical.
Half right. this can still attack carbonyl. But if it does, what's going to happen?
Oh, we can get kicked right.
What if this comes to the carbonyl, electrons up, down, and kicks that up?
Same thing.
Be the same thing. And that could be happening. If this was hydroxide, though, and that gets kicked off, that becomes a carboxylic acid, and then it gets deprotonated. So important here is you use the base here that matches this group. So if it does get kicked off, it ain't going to lead to anything new.
When using those strong bases with the aromatic compounds, how do you prevent the benzene?
If you remember benzene, it requires harsh conditions.
Oh, okay.
High temperature, high pressure. Good question. The only way we did a benzene at lower was when we used the nitrogen nucleophile.
But
And indeed, we did use LDA with the benzene before. It might be something to consider as a side reaction. Yes. Problem is, acid base tends to be faster. Also, the H's on the benzene are much less acidic. So it's like, I'm going to take this more acidic H first. And so you have a reason it's going to do something over here. Usually to do a benzene, you can't have anything else in the molecule that's acidic, or it would do that instead. Okay, so we get here, and then this can alkylate, yeah. And we can make this here. It's just a direct alkylation of this. By the way, what's the name of this? I'll do that here. That's ethyl acetate. It's got this acetyl group on it. Ethyl acetyl acetate. Sometimes called acetoacetic ester synthesis. We'll get to that though. Okay, the one thing you can do here is, and we'll be doing this a good bit, is here you can actually remove this ester group. Okay? This can be removed. And if you remove it, you're essentially replacing it with an H. We'll be looking at this mechanism. It leaves you with that there, which is that compound over there. This can be removed by aqueous acid. We'll look at how. But that's compound A, which we showed above. I didn't mention it on the previous page. Previous page, we made compound A by a direct alkylation. Here we're making compound A by an indirect, where we use this as a starting material. And this was a dummy group, activating group. Because on the previous page, we just used that and we alkylated. Why would you use a dummy group? The dummy group makes the H's more acidic. It allows you to use an oxygen base, which is more common, cheaper. You do your alkylation, then this group can be removed. This is an indirect method, and it's very common indirect method. Okay, let's look at this removal here. It's called a decarboxylation. It's actually first a hydrolysis. Okay? I could have asked you before we looked at this chemistry, what would happen if we treated that with aqueous acid? Well, you're going to hydrolyze your ester to what? To the carboxylic acid, yes. Plus ethanol. That's just a carboxylic, that's just an ester hydrolysis. But this type of carboxylic acid is not going to survive. Because carboxyl groups, and the carboxylic acid is called a carboxyl group, that have a carbonyl beta to them, just have a carbonyl beta. Well, that's alpha, and that's beta, and what is that?
No.
Okay? Are very prone to being lost as CO2, decarboxylated. The mechanism here, I may not be strictly doing it. I'm going to do it my own way. It may not be correct, I'm telling you that, but it makes sense of what we've talked about before. With heat, there's heat. With heat, imagine maybe this. These electrons move in and kick this off. Again, there's some fine details here that aren't exactly right in this exact here, but if that gets kicked off, what is being kicked off? What are we going to form here? An anion, right? Now again, you're under acidic conditions. This is not exactly right. This is more under basic conditions. But what type, does this anion have any stability?
It has more, I mean,
We can form it.
It's an enolate. And we've been talking about enolates for a while now. Because they have stability, they can be made. Yes. I really should not have done this like this. But since it says up here, the enol or the enolate can be a leaving group. And see, this can just pick up an H. If it picks up an H, we're going to have compound A. Another way to do this so we don't make a carbanion is to protonate this. Can we protonate that carbonyl? If we protonate that carbonyl first and then do this, what would that get us? That would give that. I don't like this either, but all I'm concerned about is you just jumbling up your notes. I don't mind talking through this. What's going to be over here? That becomes double bond O, right? Isn't that going to be the other side? Protonation of this makes this neutral. That's a neutral leaving group. Because if we can show resonance of this, and again, you may not even want to write this down. If we just show resonance of that, what's resonance look like? Just the enol. So what was the leaving group? The enol. Because the enol, that's the enol. That's just resonance of enol. And then whatever the minus is there, can take the H from that, and you get your enol. But what do we know about enols? Is the enol going to just exist like that?
It's a polymerization.
How do enols exist, usually? Won't the enol just tautomerize? Right? Don't enols tautomerize? I mean, that's an equilibrium. Which side's favored, the enol or the keto?
Ketone.
Keto. I mean, so if you think it through, everything just kind of gets there. Various understanding. Now, a book will maybe show this. You can actually show this. If we draw this like this instead. By the way, this has a name. We said it's an acid with a carbonyl beta. Does it say the name somewhere? Beta keto acid. You ever heard of beta keto acids? I would think you talked about beta keto acids. Is it pyruvate of beta keto acid? Have you talked about pyruvate or?
I remember pyruvate, I don't remember calling it a beta keto acid.
Show me the structure of pyruvate. Let's see if it's a beta keto acid. I think it is. It's in the anion form, that's why it's 8. Beta keto acids. Ketone bodies in your body, ketones. Well, most of the ketones have the acid as well. I mean, this is a ketone, but it's a carboxylic acid. Beta keto acid, they're very common in biochemistry. You will see them in biochemistry. Beta keto acids are prone to decarboxylating. A lot of your biochemical processes, you'll see decarboxylations. Okay? Variety of ways. Another way, this is how a textbook will usually show it is, follow the electron movement here, okay? Can you follow electron movement? If this takes the H, and these electrons move here, and these electrons move here, and these electrons move there, what does that give?
An enol.
That gives the enol plus CO2. And then the enol is tautomerizes. Okay? So this thing breaks apart. Driven by entropy, just like if I dropped a little China doll, it'll break apart. Okay? Thing breaks apart. Beta keto acid is prone to decarboxylating. I showed you different things. Anytime you make a pi bond, kick this off, that's really a stabilized thing that's coming off. Okay? In the end, do some reading. Settle on how you want to understand it yourself. And the demi group can be removed, okay, and we lose CO2. Plus ethanol, because ethanol had first had to hydrolyze your ester to the beta keto acid. Demi group can be removed. We can use a weaker base. Very common. Provide the product from the following thermolysis reaction. If you just take this here and heat it, you're going to get a different product, a different compound. What do you suggest? You can think about that. Acetoacetic acid. Well, this is also in the body. Ever heard of ketoacidosis? If you're athletes or heavy exertion, if you don't have enough I don't know if it's enough sugar or energy, your body can start producing this. Okay, it's a ketone, but that's really just part of it. It's really the acid part. You generate this acid and you become acidic, more acidic. It leads to ketoacidosis. because you're generating this. But the reason I show this, it's a beta keto acid. Okay? And that's what's formed whenever we hear the term ketoacidosis. You know, people are like, well, ketones aren't acidic. Yeah, it's not. It's the acid part that's acidic. Okay. We're out of time, guys. Pick up there. We'll continue a little bit more with this. Then we'll move into aldol reactions. Aldol reactions. See some of you in lab upstairs tomorrow. You want to choose an R group ahead of time. Let me know your team name and the R group you want.